Do you think lab-grown diamonds are real diamonds?
In fact, lab-grown diamonds are genuine diamonds in every sense, identical to natural diamonds in both crystal structure and intrinsic value. They are created inside sealed reaction chambers, where pressure, temperature, and gas composition are controlled with near-perfect precision.
Within these environments, carbon is gradually grown, crystallizing layer by layer into a true diamond.
How modern technology allows humans to create one of the world's most powerful and luxurious minerals. Natural diamonds take between 1 and 3 billion years to form under immense pressure and extreme temperatures deep within Earth's mantle. Lab-grown diamonds, by contrast, compress that process into just a few weeks inside a carefully controlled environment. What's fascinating is that laboratory diamonds are not cast like metal. They are truly grown.
The crystal develops layer by layer from carbon, sustained by energy, heat, and time. Much like a living organism,
but at the level of matter itself. From here, the idea of rarity takes on two very different meanings. Natural diamonds are rare because Earth produces only a limited amount, and that supply cannot be increased to meet human demand. Lab-grown diamonds are rare because only a handful of countries possess the technological capability, specialized equipment, and process control required to produce crystals that meet strict quality standards. So if you had to choose, would you place your trust in a diamond grown by science, or remain loyal to one forged by nature?
Today, synthetic diamonds are created using two main technologies:
high pressure, high temperature, and chemical vapor deposition. And this journey will begin with the high pressure, high temperature, or HPHT technology.
The process begins with selecting a pure carbon source, typically in the form of graphite.
It's a carbon structure with looser bonds than diamond, and easier to transform under the right conditions.
The graphite is finely ground to create a powder with uniform particle size, as this consistency determines the crystal growth capability later on. At the same time, catalyst metals such as iron, nickel, or cobalt are prepared in powder or small pellet form. From the prepared material mixture, technicians assemble a multi-layer synthetic block. Carbon powder, catalyst metals, and a tiny diamond seed are arranged in a defined structure, much like stacking layers of material to guide crystal growth. The seed is an extremely small diamond fragment that acts as the core onto which carbon atoms attach and gradually develop into a larger crystal. This entire assembly is then enclosed in a heat-resistant and high-pressure casing, typically made from special alloys or engineering ceramics. Once completed, the synthetic block resembles a compact, dense black brick, small in size but containing all the necessary physical. The synthetic block is placed into a specialized press, capable of generating pressure and temperature comparable to conditions deep within the Earth. Inside the chamber, the pressure is typically raised to around 800,000 pounds per square inch, while the temperature exceeds 2,000 degrees Fahrenheit. Under these conditions, graphite begins to dissolve into the catalyst metal,
and then recrystallizes around the diamond seed. The process does not happen instantly.
It can last from several hours to several days, depending on the desired crystal size. When the pressing cycle is complete, the chamber is gradually cooled, and the pressure is slowly reduced to prevent thermal shock that could crack the crystal. The synthetic block is then opened, revealing the diamond crystal that has formed around the original seed. After that, each crystal is examined using microscopes and optical instruments to evaluate its purity, color, and internal crystal structure. Stones that meet the standards are classified by size and quality grade for different applications.
That is the HPHT technology. So how is CVD, or chemical vapor deposition, different?
Let's continue the video to find out. In CVD technology, the diamond seed is the absolute foundation of the entire process.
These are extremely thin diamond plates, often only a few hundredths of an inch thick.
The surface of the seed must be polished at a microscopic level to ensure that new carbon atoms attach in the correct crystal order.
The seed is placed onto a specialized holder inside a vacuum chamber, precisely fixed in both position and crystal orientation.
After the seed is secured inside the chamber, the system begins.
Pumping a gas mixture into the vacuum environment. The two main components are hydrogen and methane.
In this environment, carbon does not exist as a solid or liquid, but is instead suspended in space in gaseous form.
Once the gas mixture becomes stable, the system activates plasma using microwaves or high voltage.
The plasma has a distinctive bright glow and extremely high temperature, but the heat that directly affects the seed is precisely controlled to avoid damaging the crystal structure.
When free carbon atoms appear in the plasma, they begin to move and attach themselves to the surface of the diamond seed.
Here the carbon rearranges into the correct diamond crystal lattice, layer by layer, much like constructing a building from the smallest bricks imaginable. Hindrance. This process is slow but extremely precise. Each layer is only a few atoms thick. It is this careful
To achieve very high purity and uniformity.
Unlike HPHT, where carbon is forced to crystallize under pressure, CVD builds the diamond from the top down, similar to 3D printing at the atomic level.
That is the journey of creating lab-grown diamonds. But have you ever wondered how natural diamonds are formed and processed?
Let's find out right now. Unlike the familiar sparkling image we often see, diamonds originate from an environment so extreme, it's almost hard to believe. They aren't formed near the Earth's surface,
But deep within the mantle, at depths of 90 to 120 miles.
where temperatures can reach up to 2,000 degrees Fahrenheit and pressures exceed 50,000 atmospheres. Under these extreme conditions, carbon atoms, one of the most common and basic elements on Earth, are compressed so intensely that their molecular structure rearranges completely, forming the strong and stable crystal lattice we know as diamond. However, this unique combination of conditions is extremely rare. If even one factor is missing, just a slight drop in pressure or temperature, the carbon doesn't become diamond, but instead turns into graphite,
a soft material found in pencil cores. Because of this rare formation process, diamonds only exist in the deepest, most stable
and ancient regions of the Earth's mantle. After spending millions of years buried underground, a small number of these diamonds are through ancient volcanic eruptions. They travel upward through vertical magma channels and eventually become trapped in a special type of rock called kimberlite.
That's where humans begin their search, uncovering stones that were formed between 1 and 3 billion years ago.
Now lying hidden beneath the Earth, waiting to be discovered. The journey of bringing diamonds from deep within the Earth to the surface begins with exploration.
To locate potential mining sites, geologists' reading sites rely on a combination of advanced datasets.
Gravity sensors detect shifts in underground density, and magnetometers identify magnetic anomalies that may signal the presence of deep rock formations. Sometimes even a tiny fragment of kimberlite, a volcanic rock known to host diamonds, mixed into surface gravel is enough to justify an At major open-pit mining sites, massive spiral-shaped excavations are carved into the earth, some more than a kilometer wide, and
before each blasting cycle, dozens of high-powered drills bore deep into the rock to insert explosives.
Once detonated, the shattered rock is loaded into ultra-heavy dump trucks and hauled to the surface for processing. In areas where diamond deposits lie deeper or the terrain is too difficult for open-pit operations, underground mining is used instead. Here, workers descend into narrow tunnels stretching as far as 2,600 feet below ground, where conditions are hot, humid. All of this effort, from data analysis to deep earth excavation, is in pursuit of just a few tiny gems. On average, around 250 tons of rock must be processed to yield a single carat of diamond. right after the explosives are detonated and massive rock chunks are brought up from underground.
Those believed to contain diamonds are sent straight to the crushing system, marking the first step in extracting one of the planet's most valuable minerals.
Here, giant crushing machines, each weighing tens of tons, operate like powerful steel jaws,
capable of pulverizing even granite, one of the hardest natural rocks. However, despite their extreme hardness,
diamonds are incredibly brittle. A single poorly directed impact can shatter a diamond into tiny fragments,
stripping it of all commercial and aesthetic value. For this reason, the crushing force must be carefully calibrated.
Strong enough to break the surrounding rock, yet gentle enough to preserve the diamond crystals inside.
In many modern mines, this process is divided into multiple stages, starting with slow compression using heavy rollers,
followed by rolling crushers, and finishing with vibrating separation. Each stage is fine-tuned to ensure efficiency, without risking damage to the precious stones hidden within. After the crushing stage, all the fragmented rock moves on to the cleaning phase. This step is essential because the blasted and crushed material is often mixed with large amounts of clay, mud, fine dust, privileges, and naturally occurring sticky substances. If not thoroughly removed, these contaminants can clog the machinery, wear down equipment.
To tackle this, industrial-scale washing machines are used,
including large rotating drums, multi-level vibrating screens, and high-pressure water jets. The entire mass of material is fed into a swirling water stream, which scrubs off external grime while simultaneously screening out particles that are too small.
Any fragments under 0.04 inches in size are filtered out at this stage,
as the likelihood of them containing diamonds is extremely low, compared to the cost of processing them further.
Once cleaned, the remaining material is carefully sorted by size to create what's called a concentrated ore, a collection of rock pieces that are more likely to contain diamond crystals. This is where cutting-edge separation technology comes into play. X-ray fluorescence scanners examine each stream of material in real time,
identifying the unique glow emitted by diamonds when exposed to X-rays.
As soon as a diamond is detected, the system triggers a targeted burst of compressed air,
blowing the gem out of the flow in less than a second. This method allows diamonds to be separated with incredible speed and precision,
minimizing waste and ensuring that even the smallest valuable stones are recovered efficiently.
Once separated from the surrounding rock, rough diamonds enter the preliminary sorting phase, the first step in determining the value of each individual stone.
Experts assess the diamonds based on several key criteria: size, color, clarity, and natural shape.
Sedations. While modern 3D scanners and optical tools assist in this process, much of the evaluation still depends on the trained eye.
Those who can detect microscopic cracks or subtle color variations that machines might miss.
This stage divides the diamonds into two main categories. The first group includes high-quality stones that meet the standards for luxury jewelry production. These diamonds are clear, well-shaped, and large enough to be cut into desirable pieces. Cutting tools, or high-performance components that require extreme hardness. For the diamonds with commercial potential, the journey doesn't stop here. They undergo a more detailed evaluation,
where specialists analyze their structure and flaws to plan the most efficient and profitable way to cut them.
The goal is to maximize both the economic value and visual appeal of each stone, turning a rough crystal into a... Each diamond is completely unique. No two stones are ever exactly the same.
That's why, before any cutting begins, experts perform a full 3D scan of the rough diamond to analyze its shape, internal flaws,
clarity, and how it reflects light. This data is then fed into specialized software, which calculates the most efficient and valuable cutting options. Some diamonds are divided into multiple smaller stones to maximize profit, especially if internal flaws make a single large gem less viable. Others, particularly rare or unusually clear diamonds, may be left intact to create a one-of-a-kind piece. Every decision in this stage is made with one ultimate goal:
to unlock the full potential of the diamond by balancing brilliance, symmetry, color, and weight.
All while enhancing the natural beauty that took billions of years to form.
Once the evaluation and planning stages are complete, the rough diamond moves on to one of the most crucial steps: cutting and polishing. The process begins with a preliminary cut, typically performed using a high-powered laser. With precision down to thousandths of a millimeter, the laser slices the stone along its weakest structural points, allowing it to be reshaped or divided without causing unwanted cracks or fractures. Next comes the grinding and polishing phase.
Skilled artisans use slowly rotating polishing wheels coated with diamond dust,
because only diamond is hard enough to shape itself. Throughout the process, the cutter must carefully adjust pressure, contact angles, and rotation speed to ensure each facet is crafted to the most precise proportions possible. This entire process can take anywhere from 3 to 8 weeks, depending on the diamond's size, complexity, and the desired quality standards. The final result is a stone with flawless geometry and brilliantly cut facets designed to reflect light with maximum intensity, creating the dazzling sparkle that gives diamonds their timeless appeal. After being carefully cut and polished, the diamond is sent to a grading laboratory for comprehensive inspection. At this stage, the stone is evaluated on multiple criteria, including color, clarity, carat weight, and even the tiniest internal imperfections. Each detail is examined under specialized microscopes, ensuring nothing is overlooked. If the diamond meets quality standards, it receives a microscopic laser inscription, a unique identification number engraved along its girdle, invisible to the naked eye. This ensures full transparency and traceability throughout its lifetime. Finally, trusted institutions, such as the Gemological Institute of America or International Gemological Institute, issue an official certificate. This document outlines all of the stone's technical specifications and grading results. In essence, it acts as the diamond's passport,
verifying its quality and authenticity on the international market.
Once certified, the approved diamond continues its journey into the jewelry workshop. Depending on the design, the stone may become part of a ring, necklace, pair of earrings, or even a display piece. High-end brands like Cartier, Tiffany & Company, and Harry Winston demand not only flawless diamonds, exceptional craftsmanship in every detail of the setting. Whether it involves gold, platinum, or carefully blended alloys, each finished piece of jewelry is a fusion of nature and human artistry, combining a gemstone formed billions of years ago, Vincent, with the precision and creativity of modern craftsmanship. The result is a timeless object of beauty, where the brilliance of the versatility of diamonds in modern culture, ranging from classic elegance to flashy contemporary fashion, creating something meant to be treasured for generations. From extreme pressure deep within specialized machines, to the quiet precision of atomic-level crystal growth. The journey of a diamond is a story of science, patience, and extraordinary mastery, shaped not by chance, but by carefully controlled conditions and human innovation. If you found this journey fascinating, don't forget to like, share your thoughts in the comments, and subscribe so you won't